All right, so we'll be looking at climate change implications on society, and we're just looking at how humans in the Arctic are being affected by climate change and why it's so significant. So, the Arctic, it's home to many different species. It's such a large variety, ranging from animals as small as hidden as shrimp to animals as large as known as the polar bear, which you can see over here. And so they're all living together as predator and prey. And so through their ecosystem, these animals are bringing the world a diverse population of animals which can and currently are being studied in order to further our understanding of the earth. For instance, the narwhal. Some people believe they don't even exist. They believe they're the unicorn of the sea. There's so much mystery, so much information we are yet to acquire. And so all these animals here, like Arctic foxes, narwhals, and many more which I didn't even list, they're all calling this Arctic ecosystem their homes. But however, in the past few decades, they've been facing a major threat. They're facing humans. Humans have been severely deteriorating the stability of the Arctic through climate change. We've been burning down a large amount of the world's fossil fuels. In fact, we're going to run out soon. We've been cutting down trees, destroying habitats, building factories, allowing all, like, look here, look at all this carbon dioxide being released into the atmosphere, into the world. And if you remember to the combustion unit and how we talk about carbon soot and all that stuff, we can see all of this is just being released into the world. And excuse me. And while there are many who preach about the impacts of climate change, it's still far from enough. And so the main purpose of these lessons and this media source is to really highlight the diversity of the Arctic ecosystems and show how important they are and why we shouldn't have to lose them. And so the media source actually displays the effects of what happens when molecules of carbon dioxide and other greenhouse gases are released into the atmosphere. And while it doesn't specifically show the molecules, it's showing the long-term effects. And so it displays how as ice is continuing to melt, these migrating and hunting routes are all being affected. And so like look here, look like we can see how these animals, which were, if it weren't for the melting ice, would be connected to larger bodies of ice, wouldn't have to deal with these suddenly collapsing and melting and submerging icebergs. They would not be facing such circumstances. Now, yes, I'm not. It's unfair to say that hunting wouldn't occur, but the hunting rates are being increased because of climate change. There's ice melting rapidly. These hunting routes for animals, first of all, they're being ruined, and their migrating routes are being blocked and made unusable. And the reason why I say predators can be accessing their prey easier is, as you can see here, everything is being affected. They have these set routes, these set areas in their mind. But every day with climate change, it's changing, and these unforeseeable, these what's the correct word? These unpredictable changes are costing them their lives, and it's causing everything to be shifted in a way that we don't want to be shifted. And so eventually prey will become less available. If they hunt out all of the animals, there's going to be nothing left for them to eat. And so there's so many long-term negative effects, and along with them all going extinct, we're going to be losing so much unique information. Like I mentioned before, we are still studying these animals, and studying unique animals like narwhals and making brand new discoveries is a necessity to further understand the Earth and its science. Like, again, as I mentioned, people don't even know the narwhal exists. People believe this is a horn, but in fact, you may not have even known that this is just a tusk, a tooth of theirs. And you may not have known this either, but they're actually related to orcas. There's so much about these animals that we have only just begun to touch the iceberg. See, ice and Arctic. See how it's a bad joke, but we can see just how important this ecosystem is and how we need to protect it. And so before we end this PowerPoint and we go on to look at the lessons, I want you to think about this. If we continue to harm the earth and allow these animals to face the effects of climate change, when will it be our turn? Because if climate change continues to grow as it currently is, and these animals are being affected and eventually going extinct, when will it be the humans' turns? Because humans may face extinction themselves in the near future. And so this is why climate change in the Arctic and in the world in general is so important and it's so influential and significant to society. Because unless it is dealt with and is understood and it is at least tried to be controlled and not further worsened, it will only result in catastrophe. And so now we're going to move on to the first lesson after the brief moment. All right, so now that we've understood and we've actually established the real implications of climate change in the Arctic on society, we can now get into our first lesson, which is on intermolecular forces. And so before we actually begin, what you're going to notice is a big trend of all the lessons we're going to do is that before we actually learn anything, we're going to do a quick minds on. And so for this, our minds on question for this lesson, we're going to be looking at intermolecular forces and comparing to intramolecular forces. So if you look over here, you can see that we can actually decompose the types of reactions. We can actually decompose intermolecular forces into inter and molecular forces, and then intramolecular forces can become intra and molecular forces. So basically, we have the prefixes inter and intra to compare. And so the prefix intra means within something. So for example, we talk about carbon monoxide, which has the which is CO, and so it has covalent bonds between the carbon and oxygen atoms, which is inside the molecule, with inside carbon monoxide. So then we compare the prefix inter, which means between different things, and so we can look at water, which is H2O, and we can see how it has multiple intermolecular forces acting between the hydrogen and oxygen atoms. And so, moving on to the next slide, we're going to actually begin learning about these intermolecular forces. And so sometimes you might see it says IMF instead of intermolecular forces, and that just means intermolecular forces. So no need to be no need to be confused. And so all right, so let's get into it. There are two different kinds. There are strong intermolecular forces and there are weak intermolecular forces. And so just for now, we can look at what there actually are. So we have the ionic interactions, dipole ionic interactions for the strong, and then for the weak, we have hydrogen bonding, dipole-dipole, and then London dispersion. And so these here are actually ordered in terms of strongest to weakest. And so we have ionic coming at first, and London at last. And among the weak, we have hydrogen being the strongest, and then dipole and London. So if you ever see hydrogen bonding and you are told that it's strong, that is technically a correct statement that it is strong among the weak, but in actuality, it's not a very strong bond compared to ionic interactions. All right, so with that established, we're going to take a trip back in time to 1873 to visit a Dutch physicist by the name of Johannes Diederik van der Waals. I apologize, sir, if I'm mistaken your name, but we're going to stick with van der Waals for now. And so van der Waals developed a theory to account for the properties of real gases. We don't need to know about real gases too much, but for knowledge's sake, a real gas is a gas which does not follow the understanding of the kinetic molecular theory. But again, we don't need to worry about that for now. So the main idea is that van der Waals forces were founded and named after the founder, so the van der Waals forces. And so again, we can go back. These three would be hydrogen bonding, dipole-dipole, and London dispersion. So again, strongest, then second strongest, and then we have the weakest. So starting off with the weakest of the three, we have the London dispersion. And so here we can actually see that there's London dispersion occurring between every single substance, and it's especially known to exist for nonpolar molecules. But the main point I want you to note down is that it occurs in anything and everything. And so the reason we want to note this down is because for nonpolar molecules, technically they shouldn't be having any interactions because of its structure. There is no interactions. But what makes this London dispersion so special and so interesting is that even something like this CO2 over here can be having a intermolecular force. And so what this means is that we need to remember that these particles, they aren't just sitting still like in this picture. They're all vibrating, they're moving. And so at random times, as it says here, they can shift and break the structure, making it no longer actually, no longer actually nonpolar, giving it poles. And so right now, if you may recall, the reason why this has no poles is because they're sort of canceling each other out. But let's say it were to vibrate and suddenly just knock itself over here, we would then no longer have this equal structure, and we would actually have forces acting on it. Poles would be formed, and so we would have London dispersion occurring. And so again, it is important to know that it's the weakest, but nonetheless, it is still a force, and with enough of them, it can become somewhat relevant. And so when it comes to dipole-dipole forces, which is our next one we're going to be looking at, dipole-dipole forces occur between positive and negative poles of molecules. So like we mentioned over here, how we want to have poles, positive and negatives, which can actually be interacting with each other, but these are canceling out. This is what we have here, where these are actually already been established. And so this means that we're having these positive poles interacting with negative poles. And so the reason why this happens is because opposites attract, which is something you probably heard even growing up, showing that magnets have positive sides, negative sides, and how they attract to each other. And so yeah, that's how dipole works. And again, the more you have of these small bonds, and while they may be small bonds, they like teamwork is dreamwork. So they they really work together to make a strong enough force to become significant. And so coming in at the strongest, we have actually let me go back for a second. I want to examine this more. So here we have these different poles. Now let's these different poles. So let's say we were to add another one of these over here, and we can maybe exit this. We can open up our where is it? Drawing. Oh, okay. Drawing. Give me a moment. We can open up our okay. If we can open up our drawings, we can. Okay, we're gonna line this up here. We're gonna go ahead and add another one, and so here, oh, let's make it a little thicker. Here, we're going to connect it. And so let's see here. We have a negative pole here. So if we wanted to have a force here, there would have to be a negative pole here. And then bam, we'd have a London dispersion, not London, sorry. We'd have a dipole-dipole interaction occurring between this negative pole here and this positive pole here. So to make it a little more clear, we're going to go ahead and show that this one's positive, this one's negative, and try to just copy back the drawing. You get the point though. All right, so back to this. So now that we're at hydrogen bonding is pretty important because not only is it the strongest of the van der Waals forces, but it also plays a big role in biology, as many internal structures such as polypeptide, which is a band of amino acids, which you can see over here, they have hydrogen bonds, and so hydrogen bonds only occur between hydrogen and nitrogen, or hydrogen and oxygen, or hydrogen and fluorine. And so a way that people like to memorize this is NOF. So hydrogen only can bond with NOF. And so technically this is a dipole-dipole interaction, but I'm not going to go into too deep into that. But what matters is that hydrogen can bond with NOF. And so hydrogen bonding is actually one of the factors. Of course, there's multiple, but it's one of the contributing factors to why water freezes when it cools down. And so the reason why this happens is because typically you have water molecules and you have water particles are moving more freely. As you know, solids have vibrating particles. Water has somewhat free particles, and then gas has completely free roaming particles which never collide with each other. But so when we take this water and we slow it down, we slow down the particles, these hydrogen and oxygen particles and atoms are able to interact with each other. They're able to form more of these bonds. And so this is actually why when you cool water, it freezes, it becomes a solid because stronger bonds are being made. And so I didn't want to touch too much onto the strong IMFs because we're talking about climate change, and the main point is I want to look at hydrogen bonds and ice and how they are all affected in the Arctic. But I still talk about strong IMFs a little bit. And so with the strongest of the strong IMFs, we have ionic interactions, which is stronger bonds are able to form a crystal lattice structure using positive and negative poles to create a crystal, which you can see over here is a crystal structure. And so the more ionic the molecules are, the stronger the crystal structure would be. So over here, while it isn't drawn, if you want to go back to our drawing, don't want to clear it to be honest, but I think we scroll down. Yep. So technically, let's say we were to copy these. I'm not going to do the whole thing because that'd be way too unnecessary and complicated. These would be negative, positive, negative, or some sort of arrangement like this so that these bonds can be not forcing, these bonds can be occurring and forming an intermolecular force. And so then we have dipole-dipole ionic interactions. And so these bonds occur between molecules with the dipole and then ionic substance. So for instance, we have here, okay, before I get ahead of myself, so you may want to know what's happening in this picture. And so what's happening is that dipole ionic interactions actually allow salts to be decomposed, and the correct term is dissociated, and separate the salt particles. So in this case, we have sodium chloride, and so sodium chloride, as you know, is just your everyday salt, and so typically it has strong bonds between them. However, when you introduce water or H2O, you can see that these positive charged sodiums are interacting with the negative charges of the hydrogen, and the negatively charged chlorine are interacting with the positive charged hydrogen. And so this is showing how it's all disassociating by the nearby water ions and the molecules. And so characteristics of, let me go back to present mode. So characteristics of the intermolecular forces are that, which we've touched on briefly already, but it's as intermolecular forces are occurring more and they're stronger, the more close to a solid something is. So, for instance, as we mentioned with ice, it has more hydrogen bonds when it's cooled down, which makes it closer to being a solid. And so, with this, we keep in mind that intermolecular forces determine the physical state of matter, as well as the melting point and boiling points, and some other different characteristics which we're not going to touch up, but we're not going to touch up on right now. But the main point is that they play a major role in the actual interaction of substances with the rest of the world and other forces and other factors around them. And so, as you may remember from your earlier science lessons in not even this year, just in general, the more energy something has, the faster it's moving. So again, with all these hydrogen and oxygen particles moving way faster, they're forming less bonds or weaker bonds rather. And with this, what's happening is they're melting. Their boiling point, as which we mentioned here, is the characteristics of or that IMF's determined. They're being affected. They're being reduced. They're being made weaker, and so the melting point of ice is becoming lower, and so we have these ecosystems being destroyed, as we talked about in the earlier PowerPoint, looking at how all these animals are losing their migrating routes, they're being hunted easier, and eventually going to face extinction. And so, okay, now that we've connected to climate change and we've actually gone over all the concepts, here's a consolidation question for you. And so the question is, what van der Waals forces are present in this molecular diagram of acetonitrile? There you go. So if you can see here, there's hydrogen, 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 carbon, carbon, and nitrogen. So what forces do you have here? And so let's start off with the weakest. We have London dispersion. Is there London dispersion occurring here? Take 2 seconds to think about it. The answer is yes, because as we determined throughout the lesson, London dispersion can be found in everything. So yes, there's London dispersion. Next in line we have, let's see if you remember. Okay, if you said dipole, dipole, you're correct in terms of strength. Dipole, dipole. Do we have dipole, dipole here? Yes, we do have dipole, dipole here, because while it's not labeled, I'll pull up my drawing pad again. If you may recall, let's go over here. There's actually this bond here, or this bond here between carbon and nitrogen is actually forming dipoles. And I believe if we look at our periodic tables, we can check, but give me 2 seconds. I think I can remember this. Carbon is the more less electronegative, and then nitrogen is more. And so here we have dipole-dipole interaction between this carbon and nitrogen. So yes, we do. And next in line, we have hydrogen bonding. And so we're gonna look here. Yes, we have hydrogens. Now, how do we tell if it's hydrogen bonding? We look for NOF. And while there is nitrogen here, unfortunately, it's not a bond between hydrogen and nitrogen. So no, there is no hydrogen bonding. So really quick, I'm gonna write this down so you can actually see it maybe and note it down. So London dispersion. Yes. Dipole, dipole. Yes. Hydrogen bonding. No. No. So I'm gonna go ahead and pause the video and note that down. You can go ahead, but if not, I do believe that's the end of this lesson. And so for you, I'll see you in a second. For me, I'm gonna take a quick break. Again, you yourself should take a break, even if it's just a video. Let the information sink in, test yourself, maybe look at some different examples online, or even just check your knowledge on previous lessons and previous concepts, which may help. For instance, looking at electronegativities, how just now I had to quickly touch up on my information from previous lessons, and anything that will help you just understand these concepts, as they really are important for climate change and connecting them to the Arctic and society. Okay, see you in the next lesson. Alright guys, so for this lesson we'll be looking at concentration. And so I know that when you go into a new unit, it's not as fun to just go right into the information. And so I'll go with something that's somewhat going to work your brains, but it shouldn't work you too hard. And if it does, don't worry about it. eventually we're going to learn the answers and then we won't have to work as hard. All right, so for this minds on question, I want to ask you guys, what is the difference between these two images? Now, don't be afraid to take your time and take your thoughts and just spend as much time as you need thinking about it. But don't worry if you get it wrong or if you think you're going to get it wrong, because we're going to go over this. And as I said, when we're done with this, we're all going to know how to answer these questions very easily. All right, so pause the video for 5 or so seconds, and then I'll see you when you're back. Okay, welcome back. So the answer to this question is actually that the flask here on the left is more concentrated than the flask here on the right. And so while you guys don't actually know what concentration means, you should remember from grade 8, I believe, that you should be able to dilute the solution by adding more solvent. And so in case you forgot, a solvent here is a substance that dissolves a solute. Examples: water and ethanol. And solutes are the substance dissolved. So examples are water and sugar. And so with this, when a substance has more solute, let me repeat myself. Okay, 3, 2, 1, go. And with that in mind, when something is more concentrated, this just means that it's less diluted and has a higher amount of solute than in the other flask. So as you can see here, these are the solutes inside this solution over here, which is a lot more than this flask over here. Hence the reason why this one on the left side is more concentrated than the one on the right side. And so this will all make more sense later on, so don't worry about too much about it. And so let's move on. And here you can see a picture to give you more example in case you forgot what a solute and solvent is. And so actually, before we move on, something interesting that you might want to think about is the chemistry concept of concentration and the mental concept of concentration being the same. So what I mean by this is that when you're trying to stay concentrated about a certain task, you have a solute of motivation, which is what you're trying to stay focused on your task. Meanwhile, you have the solvent of thoughts, these different tasks you want to do, like maybe go play for soccer, play games, do your homework. And so in terms of concentration, the more solvents or more thoughts you have in comparison to the solutes, which is your motivation to do the work, the less concentrated you are. If this confused you more, I apologize, but don't worry about it. Once we go through the lesson, you probably understand it a lot more and be able to say, oh, so that's what he meant. All right, so in its basic form, concentration is looking at the amount of solute in proportion to the total solution. And so like this formula over here, we have quantity of solute over quantity of solution times 100 equals concentration. And so we can actually express this formula in 3 different ways. And so one of the ways you can express it is through percentage concentration. And so with percentage concentration, we look at the volume and mass of a solution and solvent. So here you can see that there are 3 different ways to actually go about percentage concentration. And so if you go to your local pharmacy, you can easily find these examples like mass over volume form concentration, as you find some medications that are going to be units of grams per milliliter or milligrams per milliliter. And so I apologize for this horrible font here. It's supposed to be lowercase, but I'm sure you guys know what I mean by G and ml in terms of grams and milligrams and milliliters. Did I say milligrams? Milliliters, and then liters over here. So my bad for the horrible font, but I'm sure you guys get the idea. The point is that you want to be using milliliters instead of liters. And so the reason why this makes sense is because let's say you would go to the pharmacy and to buy some medication. You wouldn't be buying a giant jug, or you wouldn't be buying liters of this medication. You'd be buying milliliters. So this is why it makes more sense to use milliliters instead of liters. It's just far more practical. And so just remember this, don't use liters because it's not practical. Okay, moving on to the second way to express concentration, we have very low concentration over here. And so as per the header, you would use this type of concentration for very low amounts of solute in the solution. And so you use these two in a very similar way, but the only difference is that, as you can see here, this is parts per million, so it's times 10 to the 6, while this one is parts per billion, which is 10 times the 9. And so you may be wondering, how do you know which one to use, or why are there 2 different ones? And so the reason there's 2 different ones is because when you have a far smaller number, using parts per billion is just going to be a lot better than parts per million, because their values are just different by quite a bit. As you can tell, a million and a billion is a large difference. And so the less the concentration you have, the more likely you're going to want to be to use parts per billion, but it truly doesn't matter as long as you specify which one you've used for the sake of going backwards and actually for the sake of going backwards and actually understanding what calculations occurred. And so let's go over here for a second. And if you can see in this picture over here, this This ultra silver substance has colloidal silver and it has 5,000 parts per million of it. The reason why you would write 5,000 parts per million rather than its actual value is because its actual value would be 0.000. Okay, let me make sure I keep track. 0.000005, which is just far too complicated. So just putting 5,000 parts per million is just better for everyone. Alrighty, so now the last type of concentration we have here is molar concentration. And so you will see these mostly throughout the year because they're just they're not more important than the others, but they're just more focused on throughout the year. And so this doesn't make it any more important than the others, but just know that we'll be using these more than the other ones. So when it comes to this, you have the formula of concentration equals moles of solute over moles of solution. And so you can put this into its letter units as C or M because C is for concentration while M is for molarity. So you might see C equals N over V, you may see M equals N over V. Just know that they both mean the same thing, which is concentration. Once again, I apologize, this N should be a lowercase, but if you just write into your notes that it's a lowercase, I'm sure it will be fine. And in the future, if there's any complications, I'll be sure to clear it with you guys. Alright, so going back to this image over here, we can see how we went over how there was 5,000 parts per million, but I put this picture over here because I wanted you guys to look at how there's milligrams per milliliters. And so going back to the very low concentration, oh no, I apologize, going back to percent concentration, you see how this milligrams per milliliters, gram per milliliters, and it just shows how we just don't use liters because it's impractical and it's just far better to use milliliters. All right, so now to consolidate your thoughts, and I apologize. Before we begin, if you want to go ahead and take 5 seconds, maybe take a breather. It's quite a bit of information, and then you can come back and we'll go into these questions. All right, so now that you've had your break, we'll be going through these questions using the formulas we saw just now over here. And believe me, once you do it, it's going to be very simple and you're going to understand it just like that. All right, so for number one, we looked at what is the percent concentration of rubbing alcohol in a solution that contains 275 grams of rubbing alcohol in 500 grams of a solution? And so over here, okay, ignore all this stuff down here. So over here, you'll see that we have, if we go back to the formula, you'll see that we use mass over mass, volume over volume, or mass over volume. But in this case, we're using mass over mass because we have grams. That's, you can tell it's mass. And so what we're going to do here is we're going to do mass divided by mass times 100 to calculate the percentage. And so remember, we're going to use grams per milliliter or milligrams per milliliter, not liters. But because we're not using liters at all or milliliters at all, we'll be just calculating straight off right off the bat as 275 over 500. In the scenario that you ever find out, or you don't find out, but in the scenario that you ever see 275, let's say milligrams instead of grams, be sure to convert it because we just want to have the same units. It just makes everything make sense, and without doing it, it wouldn't actually give you the correct answer. Okay, so going back into here, we have 275 over 500 times 100 equals concentration percentage. And so 275 over 500 gives us 0.55, and then we multiply it by 100 to get the concentration percentage, which is 55%. And so I didn't put it here, but for this question, if you were to have it on the test, if it was more of a short answer, you would have to put a therefore statement, which would be therefore, let's go back to the question. Therefore, we have a 55% concentration of rubbing alcohol in a solution of 500 grams. Something like that. You know what a therefore statement looks like. And so let's get into number 2 now. So we have tap water contains 20 milligrams of lithium. Express this as parts per million in a 1 gram solution of water. And so going back to the slide, we see that we want to have these units matching. And so in this question, we don't actually have the matching. We have milligrams and grams. And so you'll see over here that that's incorrect. We want to have them converted. And so I decided to use grams. And so we did 20 milligrams equals 0.02 grams. And then we inputted back into the equation. So it's 0.02 grams over 1 gram times 10 to the 6 because we're using parts per million, as you'll see over here, parts per million, which is 10 to the 6. And so we get a concentration of 20,000 parts per million. Pretty simple, right? Now that you look at it, I'm sure it makes a lot more sense because we can see it's really just simple mathematics and just inputting numbers into these equations. All right, so now going into number 3, you're given 1 gram of Kool-Aid powder and are told to make a drink using 100 milliliters of water. What is the molar concentration of the solution? And so naturally, I don't expect you guys to know what the molar mass of Kool-Aid is. And so I provided you here. And so it's 342.3 grams per mole. And so over here, again, okay, let me go back, make sure I go through everything nice and slowly. So again, for molar concentration, we want to use moles per liter as our units. And so in this question over here, we're given milliliters, which is why I striked through this thing. Oh my God, I strike through this solution, this constant, which is why I strike through this equation over here because it doesn't use moles per liter. And so you can see over here that I converted the 100 milliliters to 0.1 liters. And so this is a little bit more of a steps. And so sometimes you'll have to convert, sometimes you won't have to. Make sure you pay attention. But so what we did was we applied this 1 gram, and then we used factor label method, which if you don't remember, go back through your notes. But for time's sake, I won't go through it. So we do 1 gram times 1 mole over 342.3 grams gives us the mole of Kool-Aid. And so we cancel out the grams because they're on the bottom. You know how this works. And then we get 1 mole per 342.3 equals 0.0029 mole. But we want the concentration, so we're going to put this back into the original equation, and we get 0.0029 mole per 0.1 liters equals concentration, which is then going to result in 0.029 moles per liter. And so you would give a therefore statement once again. Therefore, let's go back to the original question. And you put, therefore, there is 0. Oh, my bad. Therefore, we go, therefore, there is 0.0029 moles of Kool-Aid powder in 100 milliliter solution. All right, guys, so now you may be wondering, why did we go through concentration? Why is concentration important in climate change? And so I'll explain to you. Through human deforestation and the burning of fossil fuels and like natural disasters and natural occurrences like tsunamis, volcanoes, and basically anything that releases any amount of greenhouse gases is making the atmospheric concentration of these greenhouse gases go up. And so in terms of carbon dioxide specifically, and over the past 171 years, we have really allowed the concentrations of CO2 to increase by 48%, which is quite a lot, guys. And like, it's crazy to think about how in 171 years, while it seems long, it's quite a short time, we have increased the atmospheric concentration of carbon dioxide by so much. And so this graph over here actually shows you it was collected in Mauna Loa Observatory in Hawaii, and so it's actually showing how it has gone up over time. And this is pretty recent, guys. So we can see it's going up. There's like, every now and then it goes maybe a small dip, insignificant dip, but overall it's going up, and it's a major problem, guys. All right, so I know it's quite a lot of work. If you have anything you want to think about, feel free to go back to the lesson. This is why I record these, so you can always go back and make sure you understand. And so for your homework, you're going to go around your house and look for concentrations. So as I mentioned, you can find the medications. Maybe you yourself can make Kool-Aid and calculate it, tell your parents, hey mom, guess what the concentration of this Kool-Aid is, Point is just think about concentrations. All right, guys, that's it for today's lesson. See you in the next lesson. All right, so welcome to the next and final lesson for this session. And so in this session, we're going to be looking at multiple gas laws. And so there are quite a few, so we can't actually look at all of them for time's sake, but we will look at some of the more key ones. And so, as we do for any new unit or new topic rather, here's a minds-on question. And so for the minds-on, you might actually be surprised to know that you know a lot more about gas laws than you think you do. And so again, I won't tell you which gas law it is because I want you guys to think about it, but answer these two questions in your head real quick. So what happens when you press down on the balloon, and what happens when you release on the balloon? So you release your finger from the balloon. And so based on these images, and I'm sure just your own experience, you know that when you press down on the balloon, it sort of indents and it gives way to your finger, but when you release it, it then regains its shape. And so this interaction between the balloon and your finger in the air can actually be summarized and explained by gas laws. And so the first gas law we're going to be looking at is comparing pressure and volume. And so if you look at this graph over here, you'll see that as along the x-axis, as volume increases, pressure decreases. And so we can see here this curve is going downwards. And so again, we look here, we see P decreases, V increases. That is the same statement here. And so this is all described by Boyle's law. And so with Boyle's law, it's important to note that as pressure changes, volume is responding inversely. And so inverse just means opposite, so that makes sense. P is decreasing, V is increasing, that's opposite. And so, for example, let's say if we have our pressure doubling, then that means our volume is going to half itself. Or if it were to triple, then we get a third. If it were to quadruple, we have a quarter. You get the idea. And so for these interactions, it's important to note this over here. And so for this interaction to remain true, temperature must remain constant. And so naturally, or not naturally, rather, just for the sake of keeping it simple, when it comes to questions, you won't see any temperature changes. However, if it doesn't state the temperature is constant or you're just unsure, it's always safe to ask because you never know what could cost you a point. And so with this all in mind, we want to note down this equation because it summarizes the relation, the relation as P1V1 equals P2V2. With that, we're going to move on to the next gas law, which is comparing volume and temperature. And so just like the balloon question, we're going to be looking at bread. And so we can actually use bread to display the interaction between the two. And so I won't tell you what it is just like before. And so I want you to think about it. How do you think volume and temperature are reacting? And I know this picture isn't the greatest, but this is just pre-baking and this is post-baking. So this is the actual bread. All right, go ahead and take a second to think about it and then pause the video if you need to again. And I'm just going to keep going. All right, so with this, we can actually see that volume is increasing in proportion with temperature. And so this is falling under Charles's law. As with Charles's law, we see that as volume increasing, temperature increases. So let's think about this. If as we put this dough, this uncooked cold bread into the oven, it is heated. And so with this, the gases within it take reaction to the temperature and the volume increases, causing the bread to appear larger. And so, just like previously how we have to have some constants, pressure and the amount of gas must remain constant. And so again, we can look at this here. We're going to note that as temperature is increasing along the x-axis, pressure is increasing as well. And so again, make sure that even if it's not stated, you ask, or if it states it's not different, you deal with it. But again, we won't be dealing with those. And so yeah, the formula for this interaction would be V1 over T1 equals V2 over T2. Moving on to the next gas law. Oh, I lied. So we are not moving on. And so okay. So if you look over here, you see that temperature is in kelvins. But you might be thinking, kelvins, we use Celsius here in Canada. And yes, while that is true, and Americans use Fahrenheit, we don't actually want this for solving for gas laws. And so the reason why this is true is because if you look at these thermometers over here, we see that Kelvin has a 0, while Celsius and Fahrenheit go into negatives. And so we don't want this. We want to have an absolute value, an absolute 0, which only Kelvin has. And so this is called the absolute scale. And so we're not going to worry about Fahrenheit, but when you have Celsius, to convert it into kelvins, you're going to add 273 to the Celsius, the Celsius value. And so we get 283 kelvins out of 10 degrees Celsius. Now notice that I said 283 kelvins, not 283 degrees kelvins or 283 Kelvin degrees. And so it just, you don't say degrees for kelvins. It just is. And so while we're talking about units, we're going to be looking here. So again, we saw temperatures in kelvins. Now volume, you want to be in liters, and it's a simple conversion. You know, you're doing this most of your life. And so pressure, we did this before in the previous lesson, but you know about kPAs and so kilopascals, and so there are ways that you can convert it. And I do believe I have this in the lesson, but if not, we can quickly go over it later on. And so, yeah, we're moving on to pressure and temperature. So looking at the graph, we see that along the x-axis, we have temperature increasing and pressure increasing. And so it is summarized by P increasing, T increasing with Gay-Lussac's law. And so we can say that temperature proportionally interacts with pressure. And so in this interaction, we want volume to remain constant because this is always something constant. So again, make sure you're certain of the whole scenario. And so we can summarize this with the formula of P1 over T1 equals P2 over T2. And I don't believe we talked about an example for this. My bad, guys. Okay, so for this, we'll be looking at popcorn. So thinking about popcorn, why does it become popcorn? It starts off as a kernel. And so using Gay-Lussac's law, we can explain this. Oh, I apologize. And so looking at popcorn kernels, as we put these kernels into the microwave or however you're heating them, the temperature is increasing. And now with this, there's water molecules inside these kernels, which they are then being heated, interacting with the temperature. And as we see, as temperature increases, the pressure is increasing. But now kernels, they don't have an absolute hard shell or outer layer. And so what happens is the pressure eventually becomes too big for the kernel to handle and it pops into popcorn. All right, so now you may be wondering, why does all this matter for climate change? And so in addition to our previous lesson where we talked about concentration and observed how the increased concentrations of the earth are being seen in the atmosphere, we can actually connect this with the gas laws because we can see that as the volume is remaining the same, as volume is remaining the same, concentration increasing, and we can see that the amounts of greenhouse gases like CO2 are being increased in the same volume. And so as this is occurring, the pressure of carbon dioxide molecules are getting trapped under the Earth's atmosphere and is causing temperatures to rise. And so the way the sun and energy works is that the sun is always trying to use up energy, but with all this built up carbon dioxide and water, which is blocking it, it sort of impedes this process and it causes it to stay back and store up. And so we can actually compare this to Mars. And so Mars has a low atmospheric pressure and a lower amounts of greenhouse gases. And so with this, Mars actually has large frozen surfaces. All right, so that basically summarizes the lesson or ends the lesson. And so we'll be going over some questions to consolidate. However, we'll only be doing one question. The other one, I gave the answer. You guys can look over on your own. It's pretty straightforward. And the third one is actually going to be your homework. All right, so going back to the first one, I'm going to go ahead and open, let me escape this. I'm going to open up Paint. And so actually, before I do that, let's read this question. So a gas occupies 12.3 liters at a pressure of 40 kilopascals. What is the volume when the pressure is increased to 60 kilopascals? And so you know that when you're working with volume, because we have liters, and kilopascals are pressures, this is going to be Boyle's law. And so we're going to go ahead and take note of this in our heads. So we're working with P1 V1 equals P2 V2. And so going back to the question, we know that we are trying to solve for volume 2. Okay, so we're going to go back to our whiteboard. Where is it? We're going to write it down and make sure I have the right. Yep, okay, so we're going to write down P1 V1 equals P2 V2. I apologize for the handwriting. I'm not used to using whiteboards online, but you know, we're all learning through it and it's okay. So, okay, going back to the question, we have all the right units we can look over. Yes, liters, yes, kilopascals, yes, kilopascals. Okay, we're all good. So we can go ahead and proceed to actually make it so we can solve this question. So we are trying to solve for V2, we can see here. So you can rearrange this equation actually. And so you note this through basic algebra. You can get rid of the P2 by dividing it from both sides and putting it onto here. So now we get the equation P1 V1 over P2 equals V2. And so now we can go ahead and input our values. P1 is 12 point, oh, what happened? Why is it so thin? So 12.3 times 40 kilopascals divided by 60 kilopascals is going to give us our new volume. And so opening up the calculator app, we can see that 12.3 times 40 equals divided by 60 is 8.2. So 8.2 equals our new volume. And so technically I was supposed to put the units, and so let's just do it verbally. It'd be pressure, so kilopascals, volume liters, and pressure kilopascals. And so with that, the top and bottom kilopascals will cancel out, leaving our units as liters. Again, my bad for not putting the units, but you guys should know this by now. And so here we have 8.2 liters of the new volume. And so we can actually double check our answer just using the laws. And so we know that as let me open this. We know that as volume is increasing, pressure, or as if let's make it make more sense. Okay, as pressure is increasing, as we saw, we went from I think 40 to 60. Volume should be decreasing then. So if we look, our pressure increased from 12. Our pressure. Let me go back to the question so we can actually pay attention. It makes sense. Okay, so as our pressure is increasing from 40 to 60, our volume went from 12.3 to 8.2. So this makes sense. It did decrease as it's supposed to. And so, all right, guys, these next questions, look them over. If you have any questions, you go ahead and ask me, or we can go to them another time. And so here, I'll give you guys a hint to use Gay-Lussac's law, and additionally, take notes of these units. And I don't believe I had it here, and you should have it in your notes, but just in case you don't, we know that 760, can I type it? There you go, okay. We know the 760 torr equals 760 millimeters of mercury equals 1 atmosphere equals 101.3 kilopascals. I don't want to make this up. I see. But whatever, you guys get the point. You should have it in your notes as well. All right, so that's it for today's session. I hope you guys learned a lot.